Hello everyone, I'm Zhenghao Chen. I'm honored here to present our paper, Unsupervised Sampling Promoting for Stochastic Human Trajectory Prediction. Human trajectories may be capricious because of its multimodal nature, and that brings long-tail effect in its distribution. Widely used sampling methods like Monte Carlo and quasi-Monte Carlo often suffers from this long-tail effect. In this paper, we present an unsupervised sampling promoting method called BO-sampler for stochastic trajectory prediction. It mines potential plausible paths with spatial optimization adaptively and sequentially to alleviate its long-tail effect without hurting the general performance. Since BO-sampler only searches for potential candidates in the space of hidden variable Z, it can be integrated with existing stochastic models, such as CVA-based, GAN-based, and so on, without further retraining. We begin with the crucial rule of human trajectory prediction in ensuring autopilot system safety. Human trajectory prediction is critical for ensuring the safety of autopilot systems. This prediction is fundamental but challenging due to the unpredictable and multimodal nature of human motion. As we strive for accurate predictions within this complexity, addressing this challenge is key for reliable and robust autopilot systems. The long-tail effect can be widely observed in human trajectory predictors. Here, we give the illustration of frequency diagram and sample trajectories of two commonly used sampling methods, Monte Carlo and quasi-Monte Carlo. In some cases, when the pedestrians would like to take sudden move, the ground truth trajectory may hide in the tail region of distribution. So, let's dive into some of the current challenges we are facing. Firstly, we must consider the impact of the long-tail effect. This phenomenon can potentially hinder the performance of the existing model, particularly when it comes to extremely rare instances. Secondly, the breadth of potential trajectories we can cover within our limited budget is of significant concern. We need to strike a balance between the wide-ranging exploration and the constraint of our resources. Lastly, we face the issue of a lack of supervised signals to guide the sampling procedure when the pre-trained model is provided. This absence may affect the efficiency and accuracy of our modeling process. Here, we give the formulation of stochastic trajectory predictor. Because the generation of trajectory is controlled by the latent variable when the model is fixed, we will try to optimize on the corresponding space Z. Accordingly, we will define the objective function as maximizing the sum of metric function D. D should be unsupervised signal, as we mentioned in current issues. We will present how our proposed framework works. Take a single loop as an example. Initially, we have W samples. Then, we need to characterize mean and variance of the objective function by a Gaussian process. They are defined in this form. If we need a new sample, a closed-form solution of the posterior distribution is given by this stochastic process. Next, BO-sampler will fit the Gaussian process. After fitting the process, it will calculate the acquisition function phi, which is defined as the sum of mean and the standard deviation of the object function weighted by beta. Specifically, if the unsupervised signal is ADE, we may rewrite the objective function like this. Finally, we will get the updated acquisition function. Then BO-sampler will maximize phi. By doing argmax, the new hidden variable is selected, as it's shown on the acquisition function map. The W+1 sample will be generated by the new generated Z. The new generated trajectory will be added to previous sample set. By doing so, the biosampler finishes one loop of optimization, and it can be executed by doing so iteratively. The exception subset is selected based on the derivation from the output of a linear model. Because linear model can be served as a good approximation of common prediction, we use a Kalman filter as the linear model here. Then we select the top 4% trajectories, which are among the most deviated from linear prediction, as the exception. Biosampler shows a significant improvement in exception subset comparing to MC and QMC. For example, on PCNet, the average performance gain rate of biosampler to MC on ADE is 19%. On FDE, the gain rate could be even over 25%. And on full dataset, biosampler still consistently outperforms MC and QMC. Here, we present the visualization of trajectories with multiple sample numbers under 20, generated by MC, QMC, and biosampler. We can see that, different from MC and QMC, whose sampling distribution is the same with all sample numbers, biosampler adaptively modifies the sampling distribution with existing samples. We give the best predictions of different sampling methods and the ground truth trajectory on 5 scenes of ETH-UCY dataset. We observe that biosampler can provide the socially acceptable passes in the low probabilities region, which is away from normal ones. Here is a demonstration of our method, biosampler. After a warm-up, it will sequentially search for the best sample candidate. The principle is balancing the exploitation of previous samples and exploration of long-tail region. We can observe that the biosampler continuously expands the covering and finally approximate the ground truth hidden in long-tail region. Alright, that's the end of our presentation. Thank you for your time. If you are interested in our work, please check out the link on this slide. Thank you.